Building an intelligent agent encounters an immediate mathematical roadblock. To optimize decisions using dynamic programming, it requires a perfect, complete model of the world. To learn using Monte Carlo methods, an agent must wait until the absolute end of an episode to tally rewards and learn anything at all. Temporal difference learning, or TD learning, provides the mathematical bridge. It allows an agent to learn directly from raw experience, step by step, entirely without a pre-existing map of the environment. This matrix compares three approaches based on requiring a full model and bootstrapping. By isolating the temporal difference quadrant, we see it relies on sample backups, learning step by step, and bootstrapping, updating current estimates based on other learned estimates. The structure of this update rule allows for a critical shift in logic. By modifying the target term, we define whether an agent learns from the actions it actually takes or those it identifies as theoretically optimal. This architecture allows agents to update their understanding of reality in real time, using current observations to refine future predictions without requiring a final outcome. This is the TD0 equation, the simplest mechanism for temporal difference learning. It updates the value of a specific state the moment a transition occurs and a reward is received. The update is driven by the TD target. This is calculated by taking the immediate sampled reward from the environment and adding the agent's current estimate of the next state's value. Subtracting the agent's old state value from this new target gives us the TD error, or delta. This measures the strict difference between the agent's prior assumption and the newly updated target. We can track how this bootstrapping mechanism functions in practice through a short numerical trajectory. We will set both our learning rate and our discount factor to 1. Both states begin with a value of 0. On the first transition from A to B, the agent receives a reward of 3. State A's new value becomes that immediate reward, 3, plus State B's starting value of 0. State A is now valued at 3. Stepping to the next transition from B back to A yields a reward of 2. Now, State B calculates its value using the reward of 2 plus the bootstrapped, newly updated value of State A. 2 plus 3 equals 5. On the final loop back to B, the agent receives a reward of 5. State A again pulls from State B's bootstrapped value. 5 plus 5 pushes State A's estimated value to 10. As the agent continuously loops through the sequence, its value estimates update, pulling future rewards backward into present calculations. This step-by-step mathematical update propagates value through the environment. The agent no longer waits for an episode to end. It possesses a fast, model-free learning engine. Evaluating state values is only half the problem. To achieve control over an environment, the agent must shift from estimating the value of states to estimating the value of specific actions within those states. The SARSA algorithm accomplishes this as an on-policy method. It mathematically evaluates and improves the exact policy that the agent is currently using to navigate. SARSA's target relies on the specific action the agent actually executes in the next state. It absorbs any randomness, exploration, or mistakes directly into its value updates. Q-Learning alters this logic. It is an off-policy method, meaning it decouples the policy it evaluates from the behavior the agent is actually exhibiting. Instead of using the action actually taken, Q-Learning calculates its target by assuming the agent will execute the absolute optimal, greedy action in the next state, ignoring ongoing exploratory behavior. This grid charts a cliff world environment built to demonstrate the difference between these two equations. Falling off the bottom edge incurs a massive penalty of -100. We task two agents to cross the grid. Both run an epsilon greedy policy, meaning they generally pick the best action, but occasionally take a random step to explore. The Q-Learning agent charts a course directly along the edge of the cliff. Because it evaluates only the theoretical optimal future, it calculates the shortest path possible. But its off-policy nature creates a blind spot. It ignores its own random exploration, meaning those occasional random steps cause it to plunge off the cliff repeatedly during training. The SARSA agent, conversely, charts a longer, wider route far away from the danger zone. Because SARSA is strictly on policy, its updates account for the random exploratory steps it is forced to take. It experiences the massive penalty, incorporates that risk into its action values, and learns a safer route. Q-Learning identifies the shortest theoretical path in the environment. SARSA prioritizes survival during learning, adjusting its path based on the reality of its own behavior. Evaluating a target policy with off-policy methods presents a mechanical challenge. An agent must calculate the value of an optimal strategy using data gathered by a different behavior policy. To bridge this gap, systems utilize weighted importance sampling. This equation weights the returns of historical trajectories based on how likely they are to occur under the target policy. The importance weight relies on a ratio. The numerator contains the probability of the trajectory under the target policy being evaluated, divided by the probability of that trajectory under the behavior policy actually used. Calculating the true probability of a sequence of states seemingly requires knowledge of the underlying state transition probabilities of the environment itself. When we expand these trajectory variables, the environment's actual transition probabilities emerge in both halves of the fraction. Moment of clarity. But the physical rules of the environment apply equally regardless of which policy the agent runs. Because these dynamics govern both policies exactly the same way, the transition probabilities perfectly cancel out. To evaluate off-policy data, the agent does not need to know the rules of the world. It only needs the ratio of its own action probabilities. Importance sampling creates a clean mathematical bridge. It allows a system to harvest historical data generated by any behavior policy and use it to refine optimal strategies completely model-free. In reinforcement control, learning is defined strictly by its reliance on the real world. Policies and values are updated online through physical interaction and raw sampling. Planning, by contrast, utilizes a simulated model of the environment. It computes values and tests thousands of outcomes offline before executing a physical move. By utilizing a simulated model, agents can intentionally explore states that would be catastrophic in the physical world, accumulating failure data without damaging actual hardware. Advanced algorithms like UC trees accelerate this offline planning phase. They apply mathematical confidence bounds to determine when to exploit a known successful path and when to force exploration into unknown sequences. State space efficiency can be refined further in deterministic environments. Consider this board. A concept known as afterstates streamlines how an agent assesses positional value. Rather than evaluating a position before moving, the system evaluates the state immediately after the agent acts, but before the opponent reacts. This allows the algorithm to group dozens of different action sequences if they all result in the exact same board setup. This process coordinates precise update targets, off-policy data, and simulated models. By leveraging these mechanisms, the system converts raw, stochastic experience into a mathematically grounded strategy for navigating complex environments.